Hello guys, welcome to this video. In this video we will be continuing all our previous explorations about all the functions and developments that we did, and in this video we shall also find out more about the properties and all the different discoveries that we can make about this exact function and the distributions that we are studying. And meanwhile there would be a lot of solved problems as well, so just head forward to the video. We can start over from there, right? And what we can do here is see, in the example we need to have t to the power m plus 1, right? So basically it suggests us, in while doing IBP, this must be the second function, so that it must be integrated, and this must be the first function, so it must be differentiated, because when we integrate t to the power m, you get a term of t to the power m plus 1, right? And we know that we want to have I of m plus 1 and minus 1. So that is why, because since both of them are algebraic functions, we are trying to choose one of them as first and one of them as second, depending on what the question is asking us. So IMN equals to, the first function remains as it is, and the second function is integrated to become t to the power m plus 1 by m plus 1, and this is going from 0 to 1, right? Minus integration of 0 to 1, the differentiation of 1 plus t whole to the power n is n into 1 plus t into n minus to the power n minus 1 multiplied by the differentiation t to the power m plus 1 by m plus 1 dt. So let us come to the next step. So we write I of m comma n equals to, so when you put in 1 here, what you get is this 2 to the power n by m plus 1, and when you put in 0 you get a 0, so this is the whole thing, minus 0 to 1 n by m plus 1 into t to the power m plus 1 into 1 plus t whole to the power n minus 1 dt. Now notice that this integral right here is basically I m plus 1 n minus 1, right? So we write that to get I mn is equals to 2 to the power n by m plus 1 minus n by m plus 1 into I m plus 1 n minus 1. So we multiply both sides by m plus 1 to get m plus 1 into I mn equals to 2 to the power n minus n into I m plus 1 comma n minus 1, and we solve for I m plus 1 n minus 1 to get 2 to the power n minus m plus 1 I mn divided by m plus actually divided by n. So this is our required answer. So this was actually a pretty easy problem, just that the terminologies were a bit complex, but other than that it was very easy and we could have solved it easily. So if you knew and if you learned the integration by parts section carefully, you would have solved this problem within a few tries, if not more. So that is a problem. So in the next problem, let us do something about box function. So let us introduce box function. So for that, what we are going to do is we are going to evaluate pi by 2 to 3 pi by 2 box of 2 sin x dx. Now what is a box function? So let me introduce that. The box function is basically given by box of x means the greatest integer less than or equal to x. So understand it carefully that whenever you have the box function, which is also called the greatest integer function or the GIF function, it means that you are going to find the greatest integer that is less than or equal to x. A few examples might help. Suppose we want to find the greatest integer of 0.5. So the greatest integer which is less than 0.5 is basically 0, because you cannot choose -1 because we already have 0 as an answer and it's an integer which is closest to 0.5. And understand that we are finding the number which is less than 0.5 and not greater than, right? Another example is if you have 1.2, obviously it would be 1. So it basically gives you the integer part. The tricky part is when you have like negative -1.2. Now the greatest integer is not really this one, but it's rather this one, right? Because what you are trying to find must always be less than the number you are given inside the box function. So in case of positive numbers or positive reals, it just gives you the integer part or the nearest integer, right? Similarly, if you have box of pi, you know that pi is somewhere around 3.14, so this one would be 3, because 3 is the greatest integer that is less than pi, correct? So I think we are clear on this, and now denote the integral by I. Which is I equals to pi by 2 to 3 pi by 2 2 sin x box dx. Okay, so to solve this problem we need to understand that the interval is from pi by 2 to 3 by pi 2, but we need to see in which intervals does 2 sin x become an integer or change integer values. Okay, because we cannot evaluate 2 sin x inside the box function because there is no antiderivative for a box function, but rather inside specific intervals 2 sin x will be box of 2 sin x in fact will be turned into an integer, because -1 less than equals to sin x less than equals to 1 is always true for all x, right? For all x belong to real. So obviously -2 less than equals to 2 sin x less than equals to 2 is true for all x belongs to R, correct? So we are trying to find out in what intervals does it become that. So what we can do here is something like this. So 2 sin x, right? So what happens at pi by 2? So at x equals to pi by 2, 2 sin x is basically equals to 2, right? Correct? And we want to find the next value where it is greater than not greater than equal to 3, right? So 2 sin x becomes 2 at x equals to pi by 2. So let's say at x equals to 3 pi by 2, 2 sine of 3 pi by 2, and 2 sine of 3 pi by 2 is basically pi by 2 is 90 degree and sine of 270 degree, and you know this is basically equals to -2. Okay, so obviously it goes from a lot of values into a lot of different values, so we need to divide it into certain intervals. So what we can do is this: we can start from the interval pi by 2, which is the lower value, and next we need to find an interval where box of 2 sin x is always greater than equal to 1 but less than 2. So what we are trying to find is an interval where 2 sin x is greater than equal to 1, that is sin x is greater than equal to 1 by 2, right? So obviously since it's an increasing function, we know that x greater than equal to pi by 6 will work, but since x is already greater than equal to pi by 2, we know that it is minimum 1, and we need to find an interval where it is like less than 2, right? So we see that 5 pi by 6 is such a number and using that we can in a similar way we can find out all the other intervals like this. Here 2 sin x is 1, box of 2 sin x actually, so 5 pi by 6 to pi will give you a 0, then pi to 7 pi by 6 will just give you a -1 because in the third quadrant it is negative, and then from 7 pi by 6 to 3 pi by 2 it will just be -2 dx. So solving this is easy because we are just going to evaluate the values at the different limits. So this is 5 pi by 6 minus pi by 2 plus 0 plus, since it's a minus we rather have pi minus 7 pi by 6, and since it's a -2 we basically have -2 into 3 pi by 2 minus 7 pi by 6. Evaluating the whole thing, what you get is minus pi by 2. You can check the answer. So it is minus pi by 2. Okay, so this one was basically an introduction to box functions. We can also do another one. Evaluate let's say e to the power box x dx. Okay, so we understand that the limit for x is 0 to 100, right? And since we have something of the kind of the box function, we understand that let f of x equals to let's say f of box x rather, which seems like a better choice here. F of box x, let this be a function which is equals to e to the power box x, right? And we understand that for all x belongs to 0 to 1, f of box x is basically equals to f of 0. Then again for all x belongs to 1 to 2, f of box x should be equal to f of 1, and in a similar way, that is similarly for all x belongs to n comma n plus 1, f of box x is equal to n. So say using this fact we can write I equals to 0 to 100 e to the power box x dx equals to, now we can divide these intervals into a lot of terms like 0 to 1 e to the power box x dx plus 1 to 2 e to the power box x dx, and we need to do this inside consecutive intervals so that we understand how to solve the problem, because otherwise we cannot apply the property of the box function properly, because it happens in between two consecutive integers only, so that the answer becomes the greatest positive integer less than or equal to x, which is 1 in this case, 0 in this case, and like that. And the last interval would be 99 to 100 e to the power box x dx, right? We can write this as a summation which is like this, which is n equals to 0 to 99, n to n plus 1, and e to the power, in between n to n plus 1, e to the power box is 6, just e to the power n dx, right? So this just gives you n equals to 0 to 99 e to the power n into n plus 1 minus n, because n into n plus 1 dx is just n plus 1 minus n. This gives you n equals to 0 to 99 e to the power n. This is basically 1 plus e plus all the way up to e to the power 99, which is a geometric series whose answer is e to the power 100 minus 1 by e minus 1, which is the answer to the integral. So you see that manipulating box function may not be that difficult, but it certainly is a way on its own. So This is how we basically understand how to do the problem. So let us do one more problem before we end this part, and then we are going to solve other problems and more difficult ones, more interesting ones from the next video onwards, which would need a lot of explanations, and I would introduce a lot of different methods of solving them. So problem 4 for this section we have given so f of x is a sine of pi x by 2 plus b, f dashed half is root 2, and 0 to 1 fx dx is 2a by pi. And obviously we are required to find the constants a and b respectively. So the question is basically to find a comma b, which are constants and not functions of anything. Okay, so they are like real numbers, right? So solution. So we are given two different conditions here which we need to find out. So firstly we see that the derivative of fx, f dashed x, should be a into d dx of sine of pi x by 2 plus d dx of b. Since b is a constant, this evaluates to a into d dx of sine of pi x by 2. Now how do we evaluate that? Let g of x equals to sine of pi x by 2, and we define two more functions. Those are g1x equals to sine x, g2x equals to pi x by 2. Okay, then g of x is basically the composition of g1 composition g2 of x, or in other words g1 of g2x, right? Using the chain rule, we know g prime x must be equal to g1 prime of g2x into g2 prime of x, right? And separately we know that g1 prime of x is basically equal to g1x for sine x, so g1 prime of x would be cosine of x, right? And similarly g2 prime of x should just be pi by 2. So putting this we get g prime of x equals to, so cosine of g2x, which is basically cosine of pi x by 2 into pi by 2. In other words, this is just pi by 2 cos of pi x by 2, right? Right. So we see that f dashed x then becomes therefore a into a pi by 2 into cosine of pi x by 2. So we go back to the problem to see that what was given. It's f dashed half equals to root 2. So let us put root 2. So putting x equals to 1 by 2 gives us f dashed of 1 by 2 equals to a pi by 2 into cosine of pi by 4, which is equals to root 2. So solving this equation we get a pi by 2 and cosine of pi by 4 is 1 by root 2 equals to root 2. Getting everything on the other side and keeping just a here, we get this is equals to root 2 into 2 into 2 into root 2 another by pi, which basically is 4 by pi, which is the answer for a. So as you can see, we have solved a, and now the second condition is 0 to 1 f of x dx is equals to 2a by pi. So second condition is 0 to 1 f of x dx is equals to 2a by pi, right? So we try to solve this problem. We know a is 4 by pi, so this function is basically let me just see the function once again. It's a sine pi of x by 2 plus b. So it's basically a sine pi of x by 2 plus b, right, dx equals to 2a by pi, or which is rather equals to 2 by pi into 4 by pi, which is 8 by pi square. This is the given equation. So let us solve the integration first. Let us solve the integral first. Call it I. So I is equals to 0 to 1 a sine pi x by 2 plus b dx. This means this is equals to a into 0 to 1 sine of pi x by 2 dx plus 0 to 1 b dx, right? Now b is a constant, so 0 to 1 b dx is simply b because the integral is 1, and in this one the antiderivative of this function would just be minus 2 by pi cosine of pi x by 2 from 0 to 1 plus b. So when you evaluate this function, what you get is this: a minus 2 by pi cosine of pi by 2, minus of minus becomes plus, so 2 by pi cosine of 0, right, plus b. So this term is 0 because cosine of pi by 2 is 0, but the cosine of 0 is 1, so it becomes a into 2 by pi plus b, which is basically 2a by pi plus b. But we are given that since 0 to 1 fx dx is equals to 2a by pi plus b, putting the value of 0 to 1 fx dx, we see that this is 2a by pi plus b equals to 2a by pi, right? Cancelling this off, we get b equals to 0, which is the answer. So a to b f of x dx would be equal to a to b f of a plus b minus x dx, right? So this is basically the property that we are going to apply, and to apply this we see that I is equal to 0 to 1 ln of 1 minus x by x dx, and you can see a is 0 here, b is 1 here, so a plus b is basically 1, and replacing x by a plus b minus x here is meaning replacing x by 1 minus x, right? So you have to replace all the x's by 1 minus x. That is what the property tells us to do. So when we do that, we see this x becomes 1 minus x and this x becomes 1 minus x, right? So when we simplify, the result is something like this: log of x by 1 minus x dx. So it seems that the 1 minus x and x just have interchange places, but this is a real benefit to us, and in the other solution to this video I will show you how to do this problem without using this property. So there are two ways to do, more than two basically, but I'm going to show you two of them, both of them interesting enough. So for this one, we have the following integral, which is 0 to 1 log of 1 minus x by x dx, which was transformed into 0 to 1 log of x by 1 minus x dx. Right? Now, notice that 0 less than x less than 1 also implies mod x less than 1, right? And therefore 1 by 1 minus x is basically equals to 1 plus x square plus x cube and all the way up to infinity, which is the geometric series, which is only valid when mod x less than 1 is valid. And in this integration region 0 to 1, it directly implies that mod x less than 1 is also true. So this can be written as n equals to 0 to infinity x to the power n. Okay. So therefore I equals to 0 to 1 ln of x into 1 by 1 minus x dx, and obviously we change it to ln of x into summation of n equals to 0 to infinity x to the power n dx, right? And once we do that, what happens is we can take this summation outside of the integral using a lot of known theorems, one of them being the dominated convergence theorem and Fubini's theorem. So we can prove that we can swap the integration and the summation sign, and it is valid here. And when we do so, what we get is n equals to 0 to infinity 0 to 1 x to the power n into ln of x dx, right? Right. So now what it comes down is to evaluate this following integral, which also can be evaluated in two ways. I can see two ways to evaluate this. So let me show you at least one right now. So let t equals to 0 to 1 x to the power n into ln x dx. In our Eilert rule, we know that algebraic and logarithmic comes first and algebraic comes second. So let us do that. So logarithmic is first and algebraic is second. We have ln of x into integral of x to the power n is x to the power n plus 1 by n plus 1, and we go it from 1 to 0, 0 to 1 basically, minus 0 to 1. Differentiation of log x is 1 by x, integration is x to the power n plus 1 by n plus 1 dx. As you know, log of 1 is 0, so first part is 0, and then if we put in 0, log of 0 is minus infinity, but then x to the power n is also 0. So basically using the L'Hopital's rule, it can be proved that this is also 0, and what we are left with is something like this: minus 1 by n plus 1 0 to 1 x to the power n dx. And again this evaluates to minus 1 by n plus 1 x to the power n plus 1 by n plus 1 from 0 to 1, which is again 1 by n plus 1, which means it is minus 1 by n plus 1 whole squared. So therefore, putting this value, we get, therefore I is equals to minus summation of n equals to 0 to infinity 1 by n plus 1 whole squared, or we can write this as minus n equals to 1 to infinity 1 by n square, right? Now, what is this series? This is one of the most beautiful series in mathematics and one of the oldest problems basically. So this series basically, just ignore the negative sign for now. We just want the value of this series. It just says you it's 1 by 1 square plus 1 by 2 square plus 1 by 3 square and all the way up to infinity. So this is called the Bessel's problem. This is called the Bessel's problem, and it was attempted by Leonhard Euler back in 1764, and he did solve it, right? And in doing so, he had made a factorization of the element sin x, and what he did was he guessed what was the front function. What he did guess was came out to be correct and was proved later by Gauss that it was indeed correct. But the value he provided to this series, that is the sum of the squares of the reciprocals of the natural numbers was pi squared by 6. So it only makes sense that when you have a bunch of rational numbers, that is 1 by 1, 1 by 4, 1 by 9, and you add all of the rational numbers, what you get is a rational number, right? But consider the fact that there are infinitely many of them, that is, you're never going to end. So you're only going to reach some limit. And remember that pi itself, even if it is a constant, it's the limit itself. So when we are actually expressing the sum of infinitely many rationals as an irrational number, it makes sense because the irrational number also has a limiting value, right? And this rational numbers also have a limiting value. So maybe both of them correspond to the same limit, right? So anyways, the proof of this series will be provided in the next video, which might be actually a very big one, but I will try to prove it and let it go there. But just understand for this fact, this is also called the Riemann zeta function. This is also called the Riemann zeta function. Okay, and Riemann zeta function is denoted as zeta of s by 1 by 1 to the power s by 1 by 2 to the power s plus 1 by 3 to the power s and so on. And this specific value is zeta of 2, which is pi square by 6. So anyways, we will discuss more in the next lecture. Thank you for watching. So please download the Breatter Maths app, which is given in the description. It is a mathematical app where you can find all the necessary statistical calculators like chi-square calculator, one variable means, population means, t-value, and much more. You can also find calculus related calculators like integration, derivatives. There is a section where you can find what's coming up next. There is a section completely devoted on mathematical notes where you can find notes on probability, statistics, calculus, and many more are there to come. In those notes, we have already explained all the examples, all the problems and theory, and we are just covering the video lessons and solutions of those here. You can check that out. Also, you can see the video solutions in a separate section where you can understand and give a feedback on what to expect next. You can ask for a problem, you can ask for a theory section as well. So please do check it out, and also do subscribe to Breatter Maths app and also its YouTube channel.